Welcome to Dev Basics with AI, where we look at how large language models, or LLMs, actually work, moving beyond the chat interface into the engineering and mathematics that power them. What problem are LLMs solving? Their core objective is next token prediction. The model calculates probabilities across a massive vocabulary to find the statistically most likely path through a sequence of ideas. This is a high-dimensional search problem, navigating billions of word combinations. For example, in Python code, for I in yields a 99.9% probability for range. Step 1 is tokenization, translating text into numbers that computers can process. This involves breaking text into chunks like words or subwords. Byte pair encoding, or BPE, allows representing any string of characters. For example, hyperlocal might be broken into hyper and local, so the model can grasp compound meanings separately. Next, we map tokens to IDs. A fixed dictionary assigns a unique index to every possible token. This is an administrative step, moving data from the human world of strings to the computer world of tensors. For example, the sentence "the cat" becomes a simple integer array, 1, 542. Embeddings turn those IDs into meaning. In the semantic space, words with similar meanings are mapped close together in a high-dimensional space. This contextual geometry represents features like gender or category, allowing the model to understand concepts like king minus man plus woman equals queen. The model acts as a function, where y equals f of x. Your prompt is the input x, and the result is y. This intelligence is found in matrices. Matrix multiplication transforms signals through billions of learned weights, acting like a digital filter where raw light, or the prompt, passes through thousands of lenses or weights. The transformer architecture is the engine, allowing for the parallel processing of entire sequences. The core layers include self-attention mechanisms, feed-forward networks, and residual connections. It uses positional encodings to know word order while seeing everything at once. Think of it as 100 experts looking at one document and simultaneously calling out key parts. Self-attention provides context awareness through dynamic weighting, focusing on tokens that define the meaning of the sentence. It creates a correlation matrix to score every word's relation to every other word. For example, in buy a bat, the word buy signals that bat is sports equipment, not an animal. Self-attention in action enables entity disambiguation, linking pronouns like she to the correct entity over long distances. It also solves the problem of vanishing gradients, where information was diluted in older RNN models, by ensuring every word connects directly to every other word, preserving context. The Softmax layer is crucial for generating output. It converts the model scores into probabilities for the next token. Temperature is a key parameter here. It spreads the probability for creative tasks or concentrates it for factual ones. The training goal is self-supervised learning, using the internet as its own ground truth. The model acts as a teacher, predicting the hidden next word. It then compares its guess to the reality. The model plays fill-in-the-blanks with every book in the world to become an expert in the patterns of language. Cross-entropy loss is the grading system. If the model assigns a very low probability to the correct word, the penalty is massive. The objective is to maximize the probability of correct tokens. If the model guesses sky is green with 100% confidence, the math punishes it severely. The mathematical view of the loss formula shows that logarithms turn tiny decimals into manageable numbers for parameter adjustments. This formula shows exactly how much smarter the model became by increasing the probability of a correct token. The training data format includes trillions of words from the web. Training on diverse sources like Python code, Reddit, and academic journals simultaneously allows the model to learn shared logic across fields. For instance, it learns that header in HTML and headline in news both represent the top important part. Backpropagation is how the model learns from mistakes. It is the reverse trip from error back to parameter updates using the chain rule of calculus. The process calculates exactly how much each weight must wiggle to reduce the error. This is like tracing a steering pull back to an out-of-alignment gear in a car's column. Gradients represent the slope of error. A gradient is a partial derivative showing the direction of error increase. It tells the model, for example, if you increase weight by 0.001, the error will go down by 0.005. It's like playing a game of hot or cold, telling the model it's getting warmer. Gradient descent is the iterative process of updating weights. The update formula uses a learning rate, or ETA, which defines the speed of learning. Updates occur in stable batches, similar to how you make tiny adjustments to your wrist, not your whole arm, when learning to throw a ball. Advanced optimizers, such as the Atom Optimizer, go beyond simple steps. It's the industry standard for deep learning, using a running average of previous gradients to gain momentum. This is like a bicycle going downhill, where it is easier to keep moving than starting from a dead stop. The training loop consists of 4 steps: forward, where the token is predicted; loss, where the error is graded; backprop, where the logic is traced; and update, where the weights are adjusted. This can take months and millions of dollars due to the trillions of multiplications involved in the forward pass. What do parameters store? They store compressed reality, capturing patterns rather than raw data. They hold statistical associations. For example, Paris is strongly associated with France, but weakly associated with a space station. This is like a MasterChef sense of balance, learned from past mistakes. There's a difference between pre-training and fine-tuning. Pre-training gives general knowledge. The model is a predictor that completes text. Fine-tuning focuses on instruction following, making the model an assistant. For example, pre-training yields a completion, while fine-tuning yields an interactive response. Inference is the use of the model. Auto-regressive generation means the model generates one token at a time, with static weights. The context window is the limit of the model's short-term memory, like a human who forgets what they read yesterday. LLMs hallucinate because they are optimized for probability, not fact. They are optimized for looking correct, not being correct. There is no grounding in reality. They just follow paths in vector space. If a statement sounds statistically likely, the model says it with confidence. Modern extensions improve LLMs. Retrieval Augmented Generation, or RAG, adds fact-checking. Tools allow the model to recognize math and send it to an external calculator. Agents handle complex logic, moving toward neurosymbolic AI, where neural networks handle language, and symbolic AI handles logic. In summary, an LLM is a massive probability machine, refined through calculus. It is the pinnacle of statistical engineering, capturing the average of human thought in a mathematical web. Thank you for watching Dev Basics with AI.